We've been looking at the idea of exhaustive search. And we just saw when we want to do this on things that don't have a finite number of choices, real valued or floating point numbers, for example, we got a problem. We need to make the step size small in terms of how many different things we sample. But as we keep making it smaller, it's going to make the search take longer and longer, because we're going to put a lot of effort into trying to find the right answer. So we'd really like to have a way of having things still be very efficient, yet find the answer we want. And it turns out for a lot of problems, we can do that using a wonderful idea called bisection search. So what do we know? Let's go back to the idea of trying to find the square root. We know that the square root of x lies somewhere between 0 and x. We're assuming x is positive just to make life a little easier for us. That's a mathematical fact. Now, what we did was we said, let's start with 0, then 0 plus a little bit, then 0 plus 2 times a little bit, and then 0 plus 3 times a little bit, trying all of those examples until we got to something that was close enough to the answer we wanted. That's exhaustive. Rather than doing that, suppose instead we say, look, we know that the square root of x is somewhere between 0 and x, so let's just pick a guess right here in the middle. Let's call that g. Let's just pick the midpoint between 0 and x and try it. Now, if we're lucky, the answer is close enough and then we're done. That's unlikely, but even if that is not the case, we have a good situation. Even if we're not close enough, we can now ask, was that guess g too big or too small? Well, if g squared is bigger than x, then we know that it's too big. Right? We know that the square root has to lie somewhere between 0 and g. And that says we can now instantly just focus on this portion. Okay? Doing that, we can again take the midpoint of that, let's call it another version of g, a new g, and again we can say, is that close enough? If not, is it too big or too small? For example, in this case, let's assume that g squared is less than x. That says g is too small. And what does that say? It says we know that the actual value has to lie somewhere between my new g and the previous g that I guessed. And again, we can pick the midpoint and guess again. If this works, and it does, this is really cool because it says at each stage of this bisection search, I'm cutting in half the size of the range of values I have to look at. We're bisecting it, which is why it's called that. At each stage, we reduce the range of values that we have to search by half. And that is going to be really powerful. Rather than just at each stage throwing away a little bit, we're cutting down the problem a big portion each time through. So, can we capture that idea? The answer is sure, and it's not that hard to do. Again, there's some code. It looks a little bit daunting, but it's really not as bad as you think. What does it say? It says, I'm going to have some value of x I'm going to start with. Okay, I'm going to pick an epsilon, which is going to tell me how close I am. And I'm going to keep track of how many guesses I did as well. I'm going to set up initially a low and high value, which are to start with 0 and the value of x. That's my range over which I want to be trying to do the computation. Okay? My answer is initially going to be the midpoint, halfway between low and high. And then what do? I run through one of these little loops where, again, I basically say, am I close enough? Okay? If this is true, then I'm too far apart. I'm not close enough. And in that case, well, I'll print out some information that tells me where I currently am. I'll change the number of guesses. I'm about to make a new guess. And if I'm not close enough, what does it say to do? It says if my current answer, squared, is less than x, I'm too small, and I'm going to change the lower end to be that guess. I'm moving up the lower end. On the other hand, if answer squared is bigger than x, then I'm too high, and I'm going to reduce the high down to be answer. Okay? And I'm just going to keep doing that. If I keep doing that, I'm going to keep chucking this thing in half. And having done either of those two pieces, I then change my answer to again be the midpoint. And I do this one more time. So I'll just keep cycling through this, cutting in half each time the size of the problem until I get to something that's close enough, we hope. Okay, let's see what happens if we do it. Here's some code in my idle system that has exactly that. Let's do this. Basically, let's start with something simple, which we said was going to be 25. And let's see what happens if we evaluate that. Look what happens. I start off, and let's look at that. I start off with a range between 0 and 25, and the answer is the midpoint. I then cut down the high end. I then cut down the high end again. I then cut down the low end. I then cut down the low end. And you can see at each stage, it's reducing the range. And after only 13 guesses, I get a pretty good guess for what the square root of 25 is. It's not exact. I happen to know it's 5. But in only 13 guesses, I got it. Remember, last time we did 50,000 guesses to get to something that wasn't, in fact, much better. In fact, wasn't even as good as this guess one had. So notice how it's cutting down the problem at each stage. All right, let's go try this other version of this, right? 1, 2, 3, 4, 5. And let's see what happens if we find, using bisection search, the square root of that. You can see it cranking along. And wow, in 26 steps, it got to something that took 1,000,000 steps the last time around. 26 steps, it gets to a pretty good approximation. Let's try something even bigger. Let's see what happens if we do that one. All right. Again, you can see if you look at these numbers how quickly it's zeroing in. In only 36 steps, it got to the square root of a pretty big number. So in fact, this does it really well. What can we observe out of this? Well, here are some things that we see. First of all, bisection search radically reduces the computation time. And this is part of that original message, that it's not just having a fast computer, it's being smart about how we think about solving the problem. And in this case, being smart about how we generate the guess is going to be really important. So when does this idea of bisection search work? Well, it should work well on problems where there's a sort of ordering property, meaning that the value of the function being solved varies monotonically with the input value. Another way of saying it is, here the value I'm looking for is g squared. That grows as g grows. And that says that there's this nice ordering of the solutions, or the potential solutions, and so picking a midpoint gives me a good way of cutting the problem in half at each stage. We're going to come back to this idea of bisection search throughout the term. It's a really powerful tool, but you can already see how dramatically it reduces the computational cost.